Okay, so in this particular study check, it says how many grams of aluminum chloride are needed to prepare 125 ml of a 0.15 molar solution. Okay, so here what you have to do is take the 125 ml, convert it into liters, all right? So that's just move the decimal point 3 places to the left. So it would be 0.125 liters, and then multiply by the molarity because it's 0.150 moles per liter, all right? So 0.125 times 0.150, that will give you the moles of aluminum chloride. Once you have the moles of aluminum chloride, you can multiply by the molar mass of aluminum chloride to convert it into grams, right? So let's see how that works out. So 0.125 liters times the 0.150 moles per liter, and then multiplied by the molar mass of aluminum chloride, and that works out to be 2.50 grams of aluminum chloride. And that's, if you go back, that the choice would be C. Okay, 2.5 grams of aluminum chloride. Now what we're going to do is take a balanced chemical equation and then apply molarity to stoichiometry, all right? And then either determine volume or moles or grams, all right? So again, you always start with what's given, write that all down, write down a plan, how you get from point A to point B, what are the equivalence and conversion factors, and here you're going to apply the rules of stoichiometry that you learned in chapter 7, the mole to mole factors, all right? So here's an example of zinc reacting with hydrochloric acid, 2HCl, to give you hydrogen and zinc chloride. So the question says, how many liters of 1.5 molar HCl will completely react with 5.32 grams of zinc? All right, so the first things first is take this grams of zinc and convert it into moles of zinc. So divide it by the molar mass of zinc, right? Once you have the moles of zinc, then from the mole factors are that you get 2 moles of hydrochloric acid for every mole of zinc, all right? So then you can convert the moles of zinc to moles of hydrochloric acid using the mole factors. Once you have done that, you can use the molarity as a conversion factor because there's 1.5 moles of the HCl in every liter of HCl, all right? So per 1 liter, you have 1.5 moles, all right? So whatever answer you get, you then divide by 1.50, and it'll look like that, right? So the first step is to take the grams of zinc divided by the molar mass to convert it into moles of zinc, all right? And then from moles of zinc into moles of HCl using the mole factors. Okay. So moles of zinc, then convert it into moles of HCl, mole factors, and then what you're basically doing is you're going to divide it by the molarity to get the volume of HCl, okay? So you get the moles of zinc, then use the mole factors, convert it into moles of HCl, and then you're reversing the molarity. The moles are down the bottom, the liters are on the numerator. Then you finally get your answer in liters. So you're applying your molarity in the last step, but you're applying the rules of stoichiometry in the other conversion factors. So these are some ways that you can apply stoichiometry as well as what you learned in gas laws. All right, so you can take if you take a gram of something and divide it by the molar mass, you get the moles of that reactant. All right. Suppose you've been given a gas problem and it's liters of the reactant, you can use PV is equal to nRT, the gas law, convert it into moles of the reactant. Or if you're given the solution volume, you can then use molarity by taking the liters and multiplying it by the molarity to get moles of the reactant. Then once you have the moles of reactant, you can use mole factors to convert it into moles of B, which is the product. If you want your answer in grams of B, the product, you multiply the moles of B by the molar mass of B. If you want its volume, if it's a gas, then again plug it in into PV is equal to nRT, and then solve for V, the volume. If you want the answer in liters of B, then what you're going to do is then divide it by the molarity, and that will give you your answer in liters of B. So there's so many ways to apply all that you have learned previously and apply it to what you're learning here in solutions. Section 9.5 deals with dilution of solution. So dilution, as you can see here in the picture, if you have a very concentrated solution like an orange juice concentrate, what you're basically doing is you are changing its concentration by adding water to it. So you're making it less concentrated and you're diluting it by adding cans of water. All right, so the same principle applies. If you have a stock solution which is very concentrated, you add water to it and you make it less concentrated, and that's the principle of dilution. So in dilution, by adding water, now the solute particles are more spread out. All right, so per square area, it's going to be less dense, less concentrated, all right, because they're more spread out. You've added more water, so the concentration will decrease. The amount will still be the same, however, the concentration will be less. So the formula used here is you have an initial concentration, high concentration. So you take a certain volume of it, and then you're adding more water, so the new volume is higher, and so you're determining the new concentration, which would be lower compared to the previous concentration. So C1V1 is equal to C2V2. So like you see, this is a very thick concentrated solution. The particles of the solute are densely packed, and then you add water, and now the concentration changes because they're more spread out. All right, so basically you're applying that C1V1 formula is equal to C2V2. So you again, just like the gas law, it's plug and chug. You write down all that is available to you among the variables and then rearrange to solve for the unknown. So you have, what is the final concentration when 0.5 liters of 6 molar HCl is diluted to a final volume of 1 liter, all right? So 0.5 times 6 divided by 1. That would give you your final concentration, all right? So 0.5 times 6, all right? So C1V1, that's 6 times the 0.5. You don't know what C2 is. You divide both sides by V2. That's 1. So basically it's 6 times 0.5, and that's your answer. Okay. So 3 molar. Now you can change this because the concentration is in terms of molarity. Instead of C1, you can make it M1, and instead of C2, you can make it M2. Okay. So what volume of a 2% mass by volume HCl solution can be prepared by diluting 25 mils of 14% mass by volume HCl? All right. So 25 mils, that's V1. C1 is 14. So 14 times 25. C2 is 2. You want to find out what V2 is. So 25 times 14 divided by 2. Okay, and that's 175 mils. What percentage mass by volume of a solution prepared by diluting 10 mils of a 9% NaOH to 60 mils? So this time you have C1, you have V1, you have V2, and you have to find out C2. So 10 times 9 divided by 60, all right? So 10 times 9 divided by 60, and you get 1.50%. What is the molarity of a solution prepared by diluting 0.18 liters of 0.6 m HNO3 to 0.50 liters? All right, so M1, V1, this is V2, and you want to find out M2. So 0.180 times 0.6 divided by 0.540. 0.2 m is the final molarity. Section 9.6, the last section, deals with what are called as colligative properties. All right, that is, when you have some impurity in a pure solvent, then what happens to that solvent is either the boiling point is increasing or the freezing point gets lowered. Especially with respect to water, if you add either sodium chloride or ethylene glycol or any of these solutes, you either depress the freezing point or increase the boiling point. And it also depends on the number of particles that the solute forms in the solution. All right. And then we are also going to look at types of solutions, whether it's a true solution, it's a colloidal solution, or is it a suspension. All right. So this depression of the freezing point, the increasing of the boiling point, osmosis, all come under what are called as colligative properties of solutions. All right. So you have solutions which are transparent to light, which the solute particles are uniformly distributed. They're so tiny, invisible to the naked eye, such as ions and molecules, and you can't filter them out or even use what is called a semi-permeable membrane, right? Semi means somewhat. Permeable means it allows some things to go through but not other things, all right? Okay. So this is a true solution, and that's salt water, sugar water, all right, where the particles are so small, invisible, you can't filter out the things. The only way you can separate out the solute from the solvent is either a process such as evaporation, etc. Okay. Colloids, on the other hand, have got slightly bigger particles. They still can't be filtered. However, you can use what is called as a semi-permeable membrane to separate out the colloidal particles from the solvent. Okay. All right, we'll stop here and continue with section 9.6 in the next video.